Hello again, folks. Today I'm going to be covering section 9293 and 94, which is about different identities and formulas. Here's the calendar just modified for our schedule through the week. All right, this video will be for Tuesday, and what would have been covered on Monday, 92, 93, 94, I'm going to cover on today, all right, 92, 93, 94. Okay, so we're just back one day. The packet that I have for you consists of these pages. Like did I do that? I moved it. There it is. Okay. This is a summary of the identities as taken from the your textbook, or what would be your textbook, and I tried to explain a little bit about each of them. It's in 2 pages though. So you'll see it says version 2 of volume 2 and volume 3, all right, and these are the rest, all right, through section 9.4. Okay. This is just a review, something that you already have, but it's a nice summary of the coordinates of each of these special angles around, and as reference angles as well, around a unit circle. And so when I get to explaining this, sum and difference, this is really imperative. So have this on hand, or at least try to commit it to memory at some point. And just, it isn't imperative, but this is a nice diagram that is from your textbook as well, which is part of the explanation of how we get sum of difference formulas, identities. Right? It's lacking a couple of things, so I'm going to sort of annotate. All right? And if you're following along, do print that out. And we'll get busy. Okay. I'll turn on the projector here to specify some details. Actually, you know what I should do? Let me just put up a white space here, a white area, to block out. Okay, as I mentioned, these are the different identities and formulas that are from these particular sections. Right? They're good to keep as a reference. All right. Basically, I'm going to try to explain this one because this one's kind of involved. That's why it has an extra diagram included. Right? And in theory, those that follow in this particular order would be derived ultimately from this, right? Including that as well. So this is kind of the tricky one, all right, and then I'll give you some examples. Here's that diagram that would be useful. All right. Not that one, although this is useful. Let me get this out of the way. Hopefully the blue will cooperate today, and the green too. Again, it would be good in the long run to commit to memory. The XY coordinates of special right angles, namely pi over 6, pi over 4, pi over 3, same as 30, 45, 60, and pi over 2. And then realize when you get into quadrant 2 and quadrant 3 and quadrant 4, they are, these coordinates x and y are based upon the references. You just would have to account for them being negative or positive in some cases, or both negative. With that in mind, take a look at this diagram. Oh boy, it's a picture, isn't it? Yep. Ooh, a little blurry. That's not too bad. See if I can get really close. All right. What's missing from this is how sum of difference would be derived ultimately. Sum of difference identities are derived from some basic information. But first and foremost, number one, the distance formula. And knowledge of the fact that there's a trigonometric relationship to x and y. So if we're talking about a unit circle, ultimately the x value would be the cosine of the angle, right? And y would be the sine of the angle. Right? Why? Because the r values that in theory would be the coefficients would just be 1, so they're superfluous. You wouldn't have to include those. Right? Now, how you get from this situation to at least one of these, right, the sum of difference identities, right, is by considering the basically the ordered pairs of points. In this case, things that are connected by red. I should use a different color, I feel. P and Q, all right, and then the same angle basically, but rotated. Therefore, it would have the same distance ultimately between the points, but from the perspective of A and B, all right. That's the real difference here. We know that if we were going to try to calculate the point, the coordinates x and y of this point, right, that by virtue of the fact that we are in the second quadrant over here, right, that we would have a negative x value and a positive y value there, right, and involving the trigonometric relationships of cosine and sine in respect of the reference angle that would be here. Right. Cosine would be adjacent over hypotenuse, and the hypotenuse would be 1 on a unit circle. So this would be cosine of the angle, and sine would be opposite of the angle. Over again, the unit circle's radius, i.e. hypotenuse would be 1, so this would be sine of theta. Right. What we can do instead, though, right, is consider these relationships just to distinguish them, because we're going to have another angle over here that's going to be another theta in theory, by the angle that would be coterminal in theory from 0 instead. So what you may notice tucked in here is an alpha. All right. So instead of calling this from the perspective of theta, we read it from, say, if that was 30, this would be 150 degrees. We'll call this cosine of alpha, right? And then the y value would be the sine of alpha specifically. Okay, I need a little bit of light, it's too dark, sorry. Put that aside, sorry. All right. Meanwhile, this other point over here, Q, that's connecting this. This point. These points, which would similarly be a positive x and a positive y, right, would start out as being an x and a y. Right. Just for the sake of clarity, since we're going to use the distance formula, let's call this particular x and y x2 and y2, and this x1 and y1, if we wanted to get the distance between those points, say. All right. This would be a cosine of theta still, right, because it's an x value adjacent to the angle. Right. And this would be a sine of theta still. Right. But again, just to distinguish it from the other one over here in quadrant 2, all right, we'll call it this, the textbook has agreed, we'll call it beta. Right? So this would be the cosine of beta and the sine of beta, respectively. Right? Now, what is going to happen ultimately is this. You could calculate the distance from this point to this point using whatever labels you like, x1, x2, y2, x1, y1, cosine of alpha, sine of alpha, cosine of beta, sine of beta, all right? But, all right, for the sake of deriving an identity, we need a comparison. So there'd be a first distance and a second distance that ultimately will be equal, right? Because we're talking about the same thing, but from alternate perspectives. So for the sake of labeling, let's call this the distance from PQ here to there, all right? And comparing that to the distance from A to B, right? which is there and there respectively. All right. What is cleverly done, all right, is that the same angle ultimately that would be represented by this line, which I'm going to highlight in green. All right, it's not to be confused with the red alpha. Unfortunately, some of the color scheme is not so hot. All right, the same angle that would be between this line in green and this line in green would be the angle here, rotated. I'm going to highlight this in black. All right, so that it is running along the x-axis. All right, it's just rotated ever so slightly. All right, so whatever the green angle is, and you can call it angle POQ. All right, from a different perspective, rotated so that the terminal side, the initial side is running along the x-axis. All right, is this angle from here to here. All right. This is why it's a fair comparison, because the distance would be preserved, right? Just, it's more convenient along the x-axis. How come? Because at least one of the coordinates, all right, and when in this case, this particular point, all right, we could call it for its own respective distance, you know, x1 and y1, all right? We could call it cosine, not of theta, but we'll call it cosine of beta. All right, which in this case, what would be the coordinate? All right, if you just shifted this down here, you wouldn't even have to bother with the trig function. You would just say that, well, it's on a unit circle, it's 1 for the x dimension, and it's 0 for the y dimension. So that's a lot easier to use, right? It's not wrong to say it's cosine or sine, but that's what the value would be ultimately, right? When you're talking about this particular point, though, it's a little bit trickier, because ultimately the way it works out is that this point would be a cosine and a sine once and again, all right? But it's going to be the difference of the two original angles involved, essentially for this reason, all right? The angle that would be POQ, the big angle that is separating these points, all right, would be ultimately the difference between angle alpha and angle beta. Okay. So when we're referring to this point, it is to our benefit to consider it as that difference. All right. So the x value would be alpha minus beta as an argument or an input, right? And the sign would be alpha minus beta. Right. Now what we have to take away from this are the x values here and y values here, the x and y values here, right? And what they were originally, all right, and what these became, all right, once the thing is rotated, all right. So I'm gonna, because there's a lot of gobbledygook here, I'm gonna basically take from this picture this much information and the coordinates as they are written in these 4 places. Sorry for the sloppiness. So let me turn this off. All right. Lighten up the room a bit. And preserve the information that is necessary. The point of P, all right, is an x and a y, all right? It's its own x2 and y2, all right? But we're calling it, for the sake of deriving this identity, its own unique angle, no harm, cosine of alpha, sine of alpha, yes, okay. Okay. The point of Q, all right, which would be x1 and y1 for this distance formula. We're calling the cosine of beta and the sine of beta. Okay. The point of A, which is an x2 and a y2, is the difference once the angle has been rotated between alpha and beta. It's still cosine, but it's alpha minus beta and sine of alpha minus beta. And the B point, for the sake of simplicity, is the outcome. This is an x1 and a y1. Right? That would be 1 for the x value, 0 for the y value. Right? What's the cosine of 0? 1. It should be y is the value of 1, right? Cosine. Yeah, okay. All right. What's the sine of 0? It would be 0, all right? You could just use your calculator, or you could use these diagrams in theory. Here's cosine. At the point of 0, the value of a cosine wave is positive 1. That's the reason. What's the sine at 0? All right. The start of a sine wave, the value of y here, would also be 0. Okay. So that's basically the information that you would need. It's a little cumbersome because you have to write this over and over again. All right, but it's a good mental exercise, and you can slowly take something ugly and complicated and whittle it down to the truth. All right, the essential. What is cool, you know? So we're going to take all of this information and slowly but surely stuff it into opposite sides of the distance formula. Once again, this is a fair comparison because although the angle has been rotated and we've changed the labels, all right, and we're using different inputs for the angle, how they're calculated, all right, they're still equivalent, all right, overall, all right. This is just the same distance from two different perspectives, and so it will be an identity. So, remind ourselves, and I'll put this in green because what else is green good for? I like the color, but it never writes well, all right. The distance formula is the square root of an x and a y subtracted and squared plus a difference in y's, a difference in x's I should say, subtracted and squared, and a difference in y's subtracted and squared, right? And the same thing would be on this side as well. All right, we'll just use the alternative A and B labels. I'm writing it wrong, sorry, Dopey. X is here, Y is here. So, the P values and the Q values would go in here. Right? The A and the B's would go in here. Right? And we'd have these two sides ultimately to say this equals that as an identity. Right? X2, right, would be the cosine of alpha here minus X1, which would be the cosine of beta. Okay. And it's squared as it would be. You have to follow the order of operations. But in the y values, you'd have the sine of alpha, respectively, and the sine of beta. Right. I'm going to stick with this side and just, crunch it until it's less ugly to a certain point. What happens when you have essentially something that is simulating a binomial? I know that for the definition of a polynomial, I can't call this a polynomial. This is trigonometric. It's it involves transcendental functions, right? Or transcendental parts, at least. all right? But it's still something that's two parts that are separated by a minus, all right? So it's more or less two terms, and if it's squared, a binomial-esque looking thing squared would produce or simulate the perfect square trinomial model. That's going to happen a lot throughout the process, right? If you're a little bit rusty, all right, I'll put it here briefly. The outcome of a perfect square trinomial is that whatever the sign is in between here, if it's minus, then it'll be minus here and minus there. If it was positive, it would be positive there and there. And you could check it by foiling, is that whatever features are sitting in place of A and B is in the model, all right, there's going to be a squared version on each end, right? So there'll be, if this is A, it'll be A squared, it'll be B squared. And the middle is always going to be twice as much as those two things multiplied. So you'd have an A and a B here, but twice as much. It's double that. And the back is always positive, and this is minus just because that's the way it was, all right? This is the outcome. Now, if you instead took cosine and of alpha and beta respectively and plopped them in those places, you're going to get something that looks like that. All right. So essentially, if this is cosine of alpha, you're going to get cosine squared of alpha. All right. And then on the far side here, you're going to get cosine squared of beta. All right. And then in between them, all right, twice as much. I'm really squeezing this in, I'm sorry. Cosine of alpha times cosine of beta. And this would be positive always at the back, and minus just to simulate what's there. All right, that's something that you can memorize, all right, or use as a reference, all right, but you get this nonetheless. That's just dealing with this chunk here, all right. A similar effect, because in this case it's just going to be sines, minus, all right, still, are still being squared. So you will have a second perfect square trinomial, but using these figures instead, all right. I'm going to squeeze it in, just out of desperation, all right. Sine squared of, let's see, pardon me, this should have been beta here. Right. Ding dong, made a mistake already. All right. Alpha beta. No, it's fine. I'm sorry. I'm talking myself out of it. I'm sorry. I was right. All right. Sine of alpha squared. All right. And then at the back, sine of beta squared. All right. And again, because it's following a similar model, a perfect square trinomial. This would be twice as much in the middle. Right. The sine of alpha. The sine of beta, and these signs in between. This is always positive at the back, and then in this case it happens to be a minus in between these. All right. What is hidden here, all right, is the Pythagorean identity. Side note. The Pythagorean identity, which is the cosine squared of an angle plus sine squared of an angle, is equal to 1. All right. Each of these has that, if you rearrange the pieces, and realize that you can legally do that because it's just separated by pluses and minuses, and there should be the original plus that is here, still there, all right? I didn't encapsulate this in a parentheses, partly because it's kind of tight as I'm writing it, and it's getting sloppy, which is my fault. But there's no need to, because you would just be distributing positives, so these signs are not going to change, all right? What you could do, if this was written a little bit neater, is, all right, look for things that are squared of the same angle type, because there's alphas and then betas, right? And just park them next to each other. And if they are ultimately this sum, you could replace them together simultaneously with the number 1, because that's what the Pythagorean identity allows for, all right? Here's the first example, all right? The cosine squared of alpha, a positive cosine squared of alpha, all right, and a sine squared of alpha, that's right here, all right, can be paired together, and in which case they would be equal to 1, all right? So it's not really canceling, it's just transforming it via the Pythagorean identity, all right? Simultaneously, all right, there is this cosine squared of beta and this sine squared of beta, both positive, all right, this plus that, all right, which if they were paired together and put on the end, all right, the result would be a second one. Oh, I ruined my marker, all right, both of which are positive, all right, so this is essentially 1 plus 1, which means ultimately you're going to get 2, all right. But before I get to that point, there is the gobbledygook that is left in between, all right. There is, and I'm going to write it in black at this point, all right, this minus 2 cosine of alpha, cosine of beta, and this one over here, sorry for the mess, all right, minus 2 sine of alpha, sine of beta. All right. Meanwhile, they're all parked underneath the still square root symbol. All right, I'll get back to that. All right. There's a little bit of inventory you could take. All right, which is to combine what you can. These, as I mentioned earlier, are both 2. All right. And then this stuff that has a coefficient essentially of minus 2, you could factor that. All right. All right. Or was it practical to do that? You could do it now or just hesitate, all right? Yeah. My instinct is, maybe do it now, all right? So if you see a minus 2 here and a minus 2 here, you could, in theory, write this much as ripping a 2 out of this term and that term, right? Not minus 2 in particular. You're going to kind of hesitate and hold it for a bit, but the cosine of alpha, the cosine of beta, minus, right, plus in this case because you distributed, the sine of alpha and the sine of beta, okay? And again, this is all underneath the house here. That's as far as I'm going to go with this, all right? Until a little bit later. I'm going to now figure out this using their respective points. Okay? And you'll see what will happen to the square root, what will happen to this 2, what will happen to this 2. Okay? For the sake of less distraction, all right, let me erase this and rewrite this a little bit neater up here, all right, just to preserve it. This is temporarily left as the square root of 2 minus 2 times cosine of alpha, cosine of beta, plus the sine of alpha, the sine of beta. Okay. Make sure that I replicated it because it's easy to make a mess. Looks like it's okay. Now, similar effects will occur here. If on this side you inputted the A values and the B values, all right, in place of x2, you would have the cosine of alpha minus beta, and x1, which would be 1, yeah. And over here, the sine of alpha minus beta, minus 0. This side would be a lot easier to deal with for that reason. All right. This is going to be something that, again, would simulate the a perfect square trinomial, because 1 is itself an example of a perfect square. It's just more or less disguised, right? So you would have the cosine squared of this difference on one side, and technically 1 squared over here, which is superfluous. All right, and in between twice as much. All right, which would be 2 cosine of alpha minus beta. This would be added and this would be subtracted because of the nature of this being a binomial with a minus in between, binomial-esque. All right, over here, since this has a 0, there's no reason to have to continue with it. And what ultimately you'll be left with is plus the sine squared of alpha minus beta. Okay. Now, once again, there's going to be a Pythagorean identity, right? Why? Because there's a cosine of something, a slightly more complicated, input, all right? But it's still cosine of something, and that is the same something. So cosine squared plus sine squared, these two things tied together are the Pythagorean identity that results in another one. All right, and now, if I just rearrange the guts that are left over here, namely the 1 squared, which is again superfluous, you don't have to write that. This 1, I could just park in front as well. It would in theory be positive. Right. And then I'm just going to write this behind it. So, minus 2 cosine of alpha minus beta. That's a beta, I swear. Okay. Clean it up a little bit. All right. This is 2 again, right? And this would be what is hanging on here, cosine of alpha minus beta. And in this case, I could, in theory, factor at this point, but I'm gonna hold on to that. All right. So I'll put this here for the sake of cleanliness here, clarity, hopefully. These are still hanging out under their own little hat here. All right, 2 minus 2, the cosine of alpha minus beta. You can see why it helps to have very large boards, right? Less erasing, and hopefully less mess from writing. If there's a reason why a person makes a mistake, and I'm certainly guilty of this, all right, it's because your handwriting is messy. All right. So don't feel bad, just get a better thing to write on, all right, and take your time. Okay, now if we have something that is a square root here, all right, and on the other side, naturally, because it's also the distance formula, a square root here, all right, we would want to rip the roof off. Right? So if you do that, all right, what would happen? What would you have to use? You would use an opposite operation as you would in algebraic techniques, right? To induce a cancellation effect. The opposite of square rooting something ultimately would be to square it, right? And the effect would be this, essentially, which is that you would have now exposed the radicand, 2 minus 2 cosine of alpha cosine of beta plus the sine of alpha, the sine of beta on one side. And a similar effect, because you can only get away with this if you're consistent. If you did that there, and you're obligated to, and you would want to anyhow, right? You would have this exposed on the opposite side. 2 minus 2 cosine of alpha minus beta. That's a B, beta. All right. And still in between here, there's an equal sign. Just shifted, sorry. All right, now what could you do? Again, try to whittle it down, make it less ugly, whatever you could pull. There is a simple trick, obviously, opposite operations adding, subtracting, right? If this has a 2 here, right, freestanding 2, and this is a freestanding 2 here as well, all right, then you can make them go away, all right, by performing the opposite operation. There would be a cancellation effect on both sides ultimately. All right, what are you left with? You are left with the factored form of this, which is minus 2 cosine of alpha, cosine of beta, plus the sine of alpha, the sine of beta, is equal to minus 2 cosine of alpha minus beta. All right. last thing again, since this is already factored, I already ripped out the 2 a long time ago. Maybe I jumped the gun, but it's okay. It's no harm done. If you divide by -2 here, this would cancel, leaving you just with that sum in this case. All right. And then again, you get away with it if you're consistent. Do the same thing here, which you would want to anyway. All right. And you'd have that reduced to like that. All right. So what do we end up with? After all is said and done, and this was naturally a tedious process, but a good exercise, you know. You have what is written here, the cosine of alpha minus beta is equal to, I'll use black just to be consistent, what is in red here, the cosine of alpha times the cosine of beta, plus in this case, the sine of alpha. There's a little bit too much flare there. Times the sine of beta. This is one example of at least, I think it's 4. No, technically it's 6. Trig identities, that is the sum of difference identity. Right? So in this case, the difference of 2 distinct angles, right, can be calculated by these products added together. Right? The cosine of alpha minus beta, just to verify here, is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta, which is, of these 6, that particular one. All right, and ultimately, all right, the others would follow suit, all right, by a similar process. All right. That's just one of them, all right? All right. Now let's do some examples together, okay? As I said, the other identities and formulas that would follow could ultimately be derived from the sums and differences. That is where the double angle comes from. The double angle would be the special case when alpha and beta happen to be equal. The reduction formula is derived from the double angle formula. And I want to say the half angle formula is derived from reduction. All right, products to sums, sums to products, all right, come from blending together sums and differences, like adding one identity to another, in a nutshell, all right? But let's get through this. Okay. If we were going to find the exact value, which is an instruction that's saying, all right, don't use your calculator as a telltale sign, right? The exact value of this relationship, the cosine of 5 pi over 4 minus pi over 6. A couple of things. If you feel more comfortable, and I tend to myself, I don't want to sort of project my own sort of deficiencies upon anybody, but what I would recommend is, if especially for things that are not committed to memory, like pi over 6 is really 180 divided by 6, which means that it's 30 degrees. It's a special right angle. This one may be a little bit less familiar because it's beyond pi over 2. Right? You can convert them to degrees. All right? What would ultimately be the case is that this is 225. If you divide it by pi over 180, you would simplify to that. All right? And this is just good old 30 degrees. All right? Anyhow, the point of all of this is that these are 2 distinctive angles, right? So rather than call them theta, which is more of a generalization, we could say that that one is alpha and that this one is beta. If this happens to be minus, all right, it would be calculated without a calculator via the identity we just derived, right? So just to put it back, all right, I'll put it in green again. All right, I think I need a little bit of light. Let me turn this one on, this is getting dark. That's a little bit better, right? I might need to put on my kitchen light. the end of the day. So, if the cosine of two distinct angles, the difference of two angles, is equal to the cosine of the first one times the cosine of the second one, right, plus the sine of the first one times the sine of the second. Right. You could put, in theory, the angle measurements that you have in here. I think in the case of 225, I would personally prefer to use the degrees at first, because then you could figure out, all right, what is that in relation to 180, and decide what the reference angle would be. So I may start with this, all right, which is to say that this is 5 pi over 4, and this is minus pi over 6, and then put them in their respective places. All right, but then remember what they translate to. As I said, this is 225 really, and this is 30, and this is 225, and this is 30. The things that are 30 are, if you have committed to memory, special right triangle relationships, so we could do those immediately. But in the case of the 225s, you have to produce the reference angle. So we need a reference angle for this one here, and for the sine incarnation of it, which means draw a picture. Right. The type of problems that you're going to get more likely are the type that will end up being a special right angle. So here is a diagram: 0, 90, 180, 270, and 360. All right. If it's 225, the angle would have to be in quadrant 3 naturally, and the reference angle here, pardon me, which is always perpendicular to the x-axis, would be the difference of 225 minus 180, right, to produce what angle would be here, which should be 45 degrees. If this is 45 and that's 90, because we've purposely made it perpendicular, all right, then that would have to be 45 naturally, and the dimensions would be 1 square root of 2. In quadrant 3, that makes this -1 square root of 2. Okay, so the value of this angle, because of where it's located in quadrant 3, ends up being the ratio of adjacent over hypotenuse, which at least initially is going to look like this: -1 over the square root of 2. That's something that you're going to have to rationalize, but leave it alone for the moment. Okay. This one, cosine of 30, right, would be here. And 30 is the 30, 60, 90 right triangle. So the dimensions would be positive square root of 3 along the x-axis, positive 1 and 2. This angle, therefore, the outcome rather, the ratio of the cosine of this angle would be adjacent square root of 3 over 2. Right? If we're going to bond these together via multiplication, there really isn't going to be an issue, but the rationalized form of this, right, would be that you rationalize a denominator with a radical, that is multiplying it by square root of 2, in this case over the square root of 2, and you get negative square root of 2 over 2. Right? If you were adding, you would want to go through that process because the denominators would match in that case. Over here, the sine would just be the opposite of 45, which is coincidentally the same ratio. Right? So this is going to be negative square root of 2 also over 2, completely rationalized. Right? The sine of 30 would be 1/2. And there you have that. Don't forget that these are going to be added ultimately. All right. If you do the multiplication before you add, and you should, because you're just dealing with one side, so an expression. All right. When you have like radicals, right, they're the same index, they're both square roots. You can, via the product rule, more or less in reverse, you could recombine them. So keep the negative on the outside. The inside guts would end up being the square root of 6, and the denominator would be 4. Okay. Just for this half of it. Over here, you're going to get a negative in this case ultimately, so I'm going to put a minus in between them. You'd get square root of 2 over 4. Okay. Now, it would be ideal to simplify by putting them over the common denominator. They're already over the denominator for us, so it won't be too hard, right? You're just going to more or less park them next to each other. This is going to be equal to negative square root of 6 minus the square root of 2 over 4. Now what should happen if all is gone, you could check, right, is check what the decimal equivalent of this would be immediately. All right? It should be something like about negative 9.66. 0.966. That's rounded, of course. Something like that. If this is correct, all right, then when you go back to the original angles in here, all right, and you do the actual arithmetic of 225 minus 30, all right, which would be what, 195? All right. Take the cosine of that and you should get that decimal. Just remember that your calculator has to be set to degree mode, all right, if you're going to enter degrees anyhow. All right. Mine is in degree mode, so I'll go with that. The cosine of 225 minus 30. I'm sorry. Is indeed that figure. All right. Negative 0.9659, so I rounded it to 66. Okay. So isn't that cool? All right. The problem with us humans, right, not to, again, make a speech, but we are not too happy with fractions, right? But they have a benefit. A square root, even though it's, you know, obscuring a lot, it still is preserving a lot, all right? An irrational number like the square root of 2 or the square root of 6, right? Square root of 2 I have committed to memory, 1.41, whatever it is, all right? It's irrational. It goes on forever and ever. So if you were including this as part of your answer, right, in this form, or rather this one more simplified, it's better, right? It's a better answer because it really is the true thing. That's just a rounded answer that, you know, makes us, you know, oddly more happy. At least me, right? So you get it one way or another, but you could do it without the calculator, and that proves that. You get the exact answer. All right. Here's another. In this case, it's not given to you, but you see the benefit of it. If you have committed to memory special right triangle relationships, when you see something like this, the cosine of 75 degrees, right, and they're asking you for an exact value, you don't sweat it. You go, all right, well, I know that I have special right triangle relationships, right? I have 30 degrees, it's 30, 60, 90, right, ultimately, and 45, 45, 90. But what that means really is that you have these things, these parts to work with, all right? All right. So when you get an angle in here as your input, right, maybe make it a sum out of 2 of these, maybe make a pair out of 2 of these. There's quite a few combos, right? In the case of 75, what could you break that into? You could make it a difference again, so it might be the difference of 45 and 30. Pardon me, the sum. In theory, you could use 90 and 15, but 15 is a half angle. All right, cosine. All right, so in this case, we're working with a sum rather than a difference, so the model that we would be borrowing, all right, the identity would be this top one, okay? The cosine of alpha plus beta in this case is the cosine of alpha times the cosine of beta minus the sine of alpha and the sine of beta. Okay, So if you insert 45 plus 30 in here to get what would be the equivalent of 75, you can always verify later with your calculator. Put a 45 wherever there's an alpha. Put a 30 wherever there is a beta. All right, and then remember your special right triangle relationships. I mean, ultimately, what is the cosine of 45 degrees? Right, that particular triangle would end up in a ratio that would be, if it's just 45, it's not merely as a reference angle, so this would be quadrant 1, you know. This is going to be positive 1 over the square root of 2, which you rationalize as the square root of 2 over 2. All right, the cosine of 30 would once again be the square root of 3 over 2. And if you multiply these together, you get the square root of 6 over 4 again. Okay. Over here, in the case of the 45s, you know that you get the same answer a lot, right? So this is going to still be in quadrant 1 because it's just 45. It's not a reference per se. All right, so ultimately it's the square root of 2 over 2, and the sine in this case would be a half. So in that case, what do you get? You get the square root of 2 over 4. Right? And in this case, this model of the identity is a subtraction, so it would be equal to the square root of 6 minus the square root of 2, all right, over 4. All right, that is an exact answer, right, not a decimal. If you wanted the decimal, all right, you could plug this in, and you could see square root of 6 minus the square root of 2. And you get something like that, right? 0.259 if you round it positive. To 3 digits, all right? Then check the cosine of 45, all right? Cosine of 75, rather. There you have it, okay? 0.259. Cosine of 75, 0.259. I hit a button too many times. All right, cool. This is a slightly more challenging problem. It's not just plug and play, but if you were asked to calculate or find the exact value, which is implying don't use a calculator, this, the sine of the inverse cosine of this relationship plus the inverse sine of this relationship. All right, a couple of things to remind you from earlier. What does it say? Chapter 8, I want to say. When we're dealing with inverses, look at what you have. All right, this is a regular function on the outside. All right, so the answer ultimately of a regular function is going to be a what? It's going to be a ratio, right? This produces an angle, right? This is an angle, ultimately. Right? And this is another inverse, because you add angles to angles, that makes sense, right? This is going to be another angle. That means that the sum of them is an angle, which is the input of sine. Ultimately, though, because this is a regular ordinary trig function on the outside, this is going to be a ratio as an answer. Now, in this case, if we're going to involve an identity, right? We're going to use the one that invokes sine in this case. instead of calling them theta and theta, right, let's make them the two distinct things. So I'm going to call this, I'm still going to get a ratio as an answer, but so that I could use an identity, all right, I'm going to call these alpha and beta respectively. So although this is a complicated input, don't get bogged down by the details, the minutiae. Just go, it's going to be an angle because it's an inverse. All right, I'll call it what it is. An angle, we'll just say it's alpha instead, and that's beta. So this is the sum of two angles involving sine. All right, that means that when I go to my identities, all right, I'm going to go to the sum that is a sine identity that is a sum of angles, and we'll use this equivalent there. All right. So the sine of an alpha plus a beta ultimately, even if it is ugly and complicated looking to begin with, is this product added to this product. Right? It is the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Sorry about the faintness, it's just easier to write on top of green. This doesn't show up very well. Now, we're going to do a little substitution. And if this is the way it works out, I'm just going to check. This is always good to double check. Sine of alpha, cosine of beta, cosine of alpha, sine of beta. If this is standing in place of my alpha, the inverse cosine, right, then I'm going to borrow information from that. All right. Let me put little partitions here. This is how I think, even if it's a little screwy. All right. I'm going to figure out what each of these things are, independently of each other. All right. And sort of write those things in these sort of columns. All right. In the case of alpha, right, information that I have to help me out here. If ultimately borrowing information from this alpha angle, right, the inverse cosine can be translated back to the cosine of an angle, alpha we'll call it, and it's equal to this ratio, right? Then I could figure out what the sine incarnation of this, using that same triangle relationship, these parts, right? Then, right, the sine of alpha, the same angle, right, would be equal to what over 2, if that's a radius, right? Well, we know of the special right triangle relationships that are involving 1, 2, and the square root of 3, right? So this is probably a 60-degree angle, I would guess. But what is it going to be ultimately? Right? Yeah, I'll draw the triangle just for reference. Right? If I just called this alpha instead of theta, right? And the x value is a 1 in this case, and the hypotenuse or is a 2, right? Then once we have those two dimensions, what would this have to be? It would have to be the square root of 3, right? If sine is opposite, it's a y value, the angle, then that's the square root of 3, right? That means that replacing this, the sine of an angle, which naturally produces a ratio, that's the ratio. It's the square root of 3 ultimately over 2. I'm just going to kind of preserve that in its own little pocket for now. All right. You could go ahead and deal with the alpha over here and just realize, well, I would have to just use that same information. So maybe I'll do that. All right. This would naturally then be just a half. All right. for this reason, all right, if the inverse cosine is equal to a half, then from the perspective of the angle, the cosine of alpha, would be 1/2. You don't have to change anything, all right? This would just be 1/2. Right? Just borrowing that information without having to manipulate it. I like sound effects. All right. Now, when you get the betas, you're going to shift your focus over here. You're going to borrow information from there. All right. So, if maybe start with this one because it's easier. All right. If the inverse sine is this ratio of 3/5. Right, just a different right triangle. That's not special. We'll just figure it out. Then sine of the angle that this is referring to, we'll call it beta in this case, is equal to this ratio of 3/5. Right, and from that, we could figure out. Well, we don't have to do anything else. We could just borrow that immediately. Right, just like over here. Right, in this case, then we're going to use 3/5. Right. But when we get to this other part over here, we're going to use the Pythagorean theorem, basically. So for this one, the logic would follow like this. If we already know that the inverse sine is 3/5, right, and therefore the cosine, pardon me, the sine of beta is equal to 3/5, then what we could do is derive, right, via the Pythagorean theorem, what cosine would be. Cosine of beta would be something over 5 in theory, because they'd have to have the same radius. We would borrow the information that we have and put it into a right triangle. Right? We know that the hypotenuse, right, is a 5, and the y value, since this is taken from sine in theory, would be 3. So you could figure out via Pythagorean theorem, right, what the x value would have to be for the sake of cosine, right? It's going to be a Pythagorean triple, right? Famously, right? Pythagorean triples are nice whole numbers, right? Like 3, 4, and 5, all right? So if we're looking for x, all right, it's ultimately the square root of 25 minus 9, which is the square root of 16, which means it's 4. Square root of 4. So a 4 would go here, and therefore we would use that here. All right, 4/5. All right. The only thing that we have to remember is that these are not being multiplied by that; they're being added ultimately. Multiply these independently first. All right. So you should have square root of 3/2 times 4/5 plus 1/2 times 3/5. All right. Just for the sake of space, let me clean up a little bit. All right. You can simplify, but in this case it would not be practical to. My instinct is always to go, all right, cross simplify 2 and 4. Don't hold off on doing that for the reason that you're going to have to add common denominators, so you don't want to have to sort of like take 2 steps forward and then take 2 steps backward. This is going to be 10 as the denominator, right? So 10/4 times the square root of 3 plus 3/10. All right. Since they're already over a common denominator, there's no reason not to combine them. All right. This would be 4 over the square root of 3 plus 3/10. All right. If you check with your calculator, I believe this is 0.933 approximately rounded. Let's see. 4 times the square root of 3 plus 3 divided by 10. Yes, 0.9928, so rounded is 9. Sorry. 9. 3. All right. Then you could go back just to verify with your calculator. All right. Type in this sequence. All right. I'm not sure if it has to be in radian mode, but I'll check. Let's see. Sine times the inverse cosine of 0.5, because that's just what a half is, right? Plus the inverse sine of 0.6, because that's what 3/5 is. Close the parentheses. Here's just the quicker way that I wrote it, or entered it. Inverse cosine of a half plus the inverse sine of 0.6. So we get, yep, 0.993 rounded. So that's correct. Okay. I would just use the calculator to verify. All right. I know the instruction says exactly. All right. Let's do a couple of these other ones and then I'll stop. So we'll use a double. Again, a double is the situation that arises when you have a sum or a difference when the angles are the same angle. So instead of calling them alpha and beta, you could just call them 2 times theta. Right? The identity would simplify. Right? So we'll be shifting our focus. All right. Finally, sorry to take this long. All right, from here down to the double angle formulas, of which there are several. All right. Okay. Suppose you were asked find the exact value of the sine of the double angle, all right, the cosine of the double angle, and the tangent of the double angle. All right. If they give you this much information, if the cosine of the angle is equal to -1/2, and the theta happens to be in quadrant 3. Right, in that instance, I would say draw a picture immediately. So take this information and draw yourself a quick picture. So here's quadrant 3, where we have naturally negative y value, negative x value. Okay. If the dimensions are -1 and over 2, then it would have to be that this is a -1 here, and this is a 2 here, and therefore this, based upon that much information, just 1/2, this would have to be square root of 3, negative. Okay, which means what? That this is a 60-degree angle in that case. All right. All right. Now, what you could do, having figured that out, right, is go right to your calculator and say, well, what's the sine of 2 times 60, right? It would be the equivalent of 120, all right? What's the cosine of 120, all right? What's the tangent of 120? But there are formulas for each of these that you can get an exact value rather than a decimal value. All right? So that's something worth the exploration, right? Just for the sake of space, let me erase this. All right. If you did the sine, all right, we could use 2 times the sine of the angle. You don't even have to know that it's 60, you just need to know where it was located. All right. And the cosine times the cosine of theta. All right. I'll put the picture back over here just for reference. All right. Square root of 3, -1, 2. That much information is enough. All right. You can infer, because it's a special right angle, that it has to be 60, but that's a reference angle, okay? what would the ratio be in respect of these conditions here, the summary of that statement, all right, if we're looking for sine, all right? Sine would be opposite of the angle, which means that this would be negative square root of 3 over 2, sorry. And the cosine, which is already given to us, is negative 1/2 times 2. All right, this is some simplifying that could go on here. Firstly, you could cross simplify at least one of the 2's. This is going to become a positive ultimately, which means that the sine of 120 degrees in theory should be equal to the square root of 2 over 2. The square root of 3 over 2. All right, and it's a positive because of the sign combinations. All right. So if that's 0.866 from rounding it, all right, square root of 3 over 2, all right, then check it. What's the sine of 120? Right? Just to verify. Yep, indeed. All right, positive square root of 3 over 2 is 0.866 roughly. All right. If you did the cosine, you have a couple of choices in the case of cosine. I'm just partial to this one myself, because it kind of looks like the Pythagorean theorem, so it's a little bit easier for me to remember for that reason. It's just that it's a difference instead. This is equal to the cosine squared of the angle minus the sine squared of the angle. We use that version of it. Okay. We already know what the dimensions would be. Right? You don't need to know the angle, you just need to know the ratio that they would equate to based upon that description. So in this case, the cosine of the angle would be 1/2 squared minus the sine of the angle is the square root of 3 over 2 squared. Okay. And in that case, I should remember this is a negative technically at this point, not to be confused with the negative, the minus that's in the formula here. Okay, what happens when you square stuff, right? Fractions, both the top and the bottom are affected by that. All right, so a lot going on here. All right. Which means you get 1 over 4 for the half, and you get a positive ultimately out of this. The 3 is revealed, and it would be minus, because of that minus, 3 over 4. Right? Which means that it's going to be minus 2 over 4, which is a negative 1/2. Right? Negative 1/2 for this one. Okay. Check out the cosine of 120, just for verification. All right. Negative 0.5, it is correct. And here's the tangent. Tangent, I think you have just one version of this, right? Okay. So here's the tangent. I'm sorry, I'm looking in the wrong place. Here's the double angle for tangent, which is, let's see, 2 tangent of the angle on top over, let's see, 1 minus tangent squared of the angle on the bottom. Okay. We can still get the same information. We're going to get a ratio, a fraction basically for this and a fraction for that. We could straighten it out. All right. Just remember to follow the order of operations. You have to square things and combine an entire denominator if we blend it together at all over the top. All right. So tangents would be what? All right. Tangents would be in relation to the angle, the y value over the x value. The opposite over the adjacent. So in that case, you would have negative square root of 3 over negative 1 squared. These being that they are, to begin with, a negative over a negative would be a positive. Right? So it's really just square root of 3 because of the denominator being 1, which means that once this is applied here, even if you did it to both pieces, you're going to get 3. Right? So 1 minus 3 means that this is a negative 2. On the bottom. Okay. And the top is the same ratio. In place of this, right? The fraction would still be opposite over adjacent, so it should be square root of 3 over 1. Negative negative is the positive, it's just square root of 3, which means that it's 2 square root of 3. And then if this is a positive over a negative, it is ultimately a negative. So that combination, the 2's would simplify. It should be the equivalent of negative square root of 3. All right. So just check, negative 0.866 is what it should be. The tangent of 120 degrees would be, pardon me, that's negative 1.7, not divided by 2. All right. So yes, negative the square root of 3 is negative 1.732. Okay. 866 is when you divide by 2. Okay. All right. All right, here's a half. If you were asked to find the sum, pardon me, find the sine, I'm reading badly, the sine of 15 degrees, you could use a half angle formula. All right, how come? Because if you remember, you have some tools in the toolbox. You have a 30-degree angle to work with, a 45-degree angle, a 60, and a 90, ultimately. What is 15 if you recognize a relationship to one of these special right angles? All right, it's 15 is half of 30. All right, so in the case of sine, the sine of half of the angle, if this is 15, ultimately overall, all right, what does that make alpha? All right, alpha is 30, which means that in the identity, all right, and I'm looking here, sine of alpha plus or minus the square root of 1 minus cosine of alpha over 2. Let's just log 30 in here, and then we can simplify it. We're still looking for, I didn't write it, but an exact value, you know. So, if you're 15, what is that implying? Quadrant 1, right? So, here is, we're going to borrow from 30, which is still also quadrant 1. To get this fraction and then simplify it. All right. Cosine is adjacent over hypotenuse, so it would be square root of 3, 1, and 2 that I'm borrowing from again. That sounds like trouble. This ratio, therefore, would be the square root of 3 over 2. Let's combine the top, if you can help it. All right. A convenient ratio of 1 would be 2 over 2. So the inside guts of this radicand, at least above the line, would be 2 minus the square root of 3 over 2, and then there's the original line here, divided by 2. It makes it a complex fraction, right? Remember, you could write it vertically as a complex fraction style of writing, or you could write it horizontally. I prefer to do it that way, personally, because I think it makes it more clear. The horizontal incarnation of this would be 2 minus the square root of 3 over 2, right, divided by, because of this line here, 2, which makes it multiplied by half, you know, keep change flip, right? Good, okay. So, what does that simplify to? Right. The top times that is just itself, 2 minus the square root of 3. The bottom times the bottom is 4. Meanwhile, this is all still hanging out underneath a radical, right? A glorified fraction, if you will. The quotient rule of radicals, remember, says that if it's a convenience to do so, you could split a fraction into two separate radicals. Maybe one of them will escape the radical, right? And that's perfect in this case, because look what happens. All right, 2 square root of 3 over 4 would be this, even if it's ugly, right, over the square root of 4, right? It may not look beautiful, but just so happens that 4 is what, a perfect square? So the square root of a perfect square radicand would produce a whole number, right? So this is what we get. It's a little bit sloppily written, I'm sorry. I'll put it here without the mess in the way. It's equal to this. The square root of 2 minus the square root of 3 all over just 2. Now, if you're trying to decide between the positive and the negative, I would argue that since this is 15 in quadrant 1, the dimensions of this would have to be a positive, right? Because both the y values and the x values are positive. Right, so to verify, again, you can put this in your calculator. Don't fall, please. I think it's 0.2 something. Let's see. On the top, the square root of 2 minus the square root of 3 embedded in it, divided by 2. Yeah, you get 0.2588, so about 2.59 roughly if you rounded it to 3 places, right? What's the sine of 15? If it's in degree mode, you're good to go. That is correct. Okay, very good. Being hailed. What is this? Okay. We'll do a reduction now, and then we'll shift gears. This one's cool, but it's kind of redundant. It's a reduction. Okay, so watch this. All right. In this case, this is an interesting thing happens. All right. The advantage of having the reduction formula is that you can take something that's an even degree. It doesn't have to be just something squared per se. It could be just an even degree higher than that, so to the 4th or to the 6th in theory. And eventually reduce it down to just degree 1. Right? Hence it's reducing, right? I think I moved my board just a little bit, sorry. All right, so if we were going to write cosine to the 4th of x is the input, right? In terms of just cosine would technically be degree 1. Nobody ever puts a 1 there. Right, but that is the outcome. We'll have something long and complicated, but it will just ultimately be cosines, which means that if you had to do it by hand and you were talking about an input that was a special right triangle relationship, you could do it without a calculator. So, all right, here's our formula. All right, we would start with this. All right, cosine to the 4th of x, all right, and then apply rules of exponents. Right. Remember when you have, from the rules of exponents, pardon me, I'll just do this, something like this. When you have an exponent raised essentially to an exponent, all right, what happens to them? They multiply, right? So kind of think about this backwards. What can I break this into, this 4, all right, that would jibe with this portion of the diagrams here, our reduction formulas. Right? Now, if we're talking about firstly cosine, all right, then look here, all right. If I'm going to use the reduction formula somehow, I got to get it to look like that. I may have to do it twice. In this case, you're going to probably have to, all right. But I'm going to borrow this information here, all right, for cosine squared. So I'm going to think about it this way. That's the outcome. Something times something that makes that involves something squared, would be 2 times 2, right? So, bad choice of letter maybe, all right? But what I'm going to do with this is essentially this. I'm going to have, in parentheses, cosine squared of what was there, the input value of x, all right? And then encapsulated in another parentheses here, all right? All right. So this is 2 to the 2, so it is originally that. Why bother? Because this, the gutsy here, all right, can be replaced with, all right, that version of the reduction formula, which notice involves a double angle. So this would be, and I'll put it in red, 1 plus cosine of, if I'm borrowing the formula to begin with, I'm going to have to make a little adjustment in a moment. Theta, all right, then it would be that, okay? Now, in this case, then I use the letter theta, right? What do they use for the input? They use x. So the one tweak that I would have to make to the identity is that I would have to put an x here to begin with, okay? All right, and now apply the exponent to what is essentially binomial-esque top here and the bottom, right? Which is not too bad, right? Because then you have something that again is behaving as the perfect square trinomial. That doesn't scare us, right? Shouldn't, right? Not in the long run, right? Something at the front squared, something at the back squared, and then twice those two things in the middle, in this case, added, right? So you would get this, right? For the guts on top, I put it in red just to be consistent. You'd have 1 at the front. It would be squared in theory, but that's superfluous, right? So I'm just going to put 1, all right? At the back, I would ultimately have this cosine squared, and I'm just going to encapsulate the 2x for the moment. So squared at the front, squared at the back, and then in the middle, according to the perfect square trinomial formula, it would be twice as much, all right? Those two things multiplied together. So it's really just 2 times 1 times cosine, all right? That base, I mean. So 2 cosine of 2x, right? The model would say this is always positive in the back, and in this incarnation of it, it would be a positive there. I'm going to get rid of that now because it's unnecessary. All right, that's the top. All right, the bottom would be 2 times itself, which is 4. All right. It will be to your benefit, I think, to kind of move this 4 maybe out in front. So you could think of it this way. If you were to write this as 3 distinct terms, right, make that what that would end up being, 1/4, right? This would reduce to a half, and that would be a quarter. All right, we'll make it a little bit easier, I think, to look at. All right, so this is, I'm gonna write it sideways too. So 1/4, that's what the 1 becomes if divided by 4. All right, plus 2/4 reduced is a half. That's the coefficient of what the middle term would be now. Cosine of 2x. And then, because there's nothing here but a 1 technically as a coefficient, it would be 1/4 again. So plus 1/4, and in this case it's squared with that input. Okay. At least it doesn't look like it has a denominator, so it's a little bit easier to deal with. We still have to do this again because if we're going to go the whole 9 yards, make everything degree 1 cosine, it's going to happen again there. All right. So, watch what happens now. All right. For this chunk of it, we'll have to repeat the process. All right. Replace that with the model. All right. It can be a little cumbersome because of the similarity between it and the formulas. All right. but don't be deterred, right? In place of this, and I don't want my thing to be in the way, but in place of this, it would be by itself, according to the identity, equal to, 1 on top again, plus cosine of the double angle. Now here's where you get a little confused, anybody naturally would, right? That's going to replace this, right? The input we have to deal with, right? The input is not theta, all right? All right? It's standing in place of theta. The theta at this point in the conversation is that it's 2x, right? If it was just theta, then it would be 2 times theta, right? As before, it was 2 times x. Now what it's going to be is that this theta is a 2x. So you have 2 times 2 in this case. So what does that mean? It means that if I'm going to write it a little bit nicer, a little bit neater, I have a quarter plus a half. Cosine of 2x remains as it was. All right, plus the quarter that was hanging out in front. All right, and then the guts here. All right, and meanwhile, this is all what? It's good. All right. 1 plus cosine of essentially 4x is the outcome here, over 2. That's what this ends up being there. Okay. Now you're going to do a similar thing, perhaps just for the sake of making it look, it's not really, but making it look sort of linear, all right, which is that maybe give each of these parts here what their denominator would be ultimately. All right. Why? Because it might make it a little bit easier to do a fraction times a fraction here. All right. And then a fraction times a fraction here. All right. Essentially, this maintains as 1/4 plus a half cosine of 2x, all right, plus 1/4, and now the guts in here are 1/2 independently, all right, and then plus, because that's what's here, a half as a coefficient of the cosine of 4x. If you distribute a quarter to this, you would be obligated, of course, to do it to that as well, but it's the coefficient times the constant as well. And then there. All right, so what do you get? You get a quarter plus a half cosine of 2x. All right, this would be an eighth, right? Plus 1/8. And then an eighth again, but in this case it has the cosine of 4x next to it. And perhaps if I analyze this and I get the gobbledygook out of the way, it could be simplified further still. Right? So combine whatever constants that we can. Say for example, there is a free floating quarter here and a free floating 1/8 here. So with a common denominator, this would be 2/8. 1 plus 2 would be 3/8 out in front. Let me get a little bit more nice, sorry. 3/8 is a number out in front. That leaves us with plus a half next, cosine of 2x. And then there was this one, plus 1/8 cosine of 4x. Now let's see if we met the conditions that we were supposed to. Looks like we did. Yeah, all right. You can take ultimately a higher degree, an even degree, all right, and via the reduction formula, express it in terms of just degree 1 cosine. All right. So that's kind of cool, right? All right. Now the last thing will be a product of sum and a sum to product. These are derived from blending together, basically adding a sum or a difference formula, identity, to another one. All right, you can derive the product of sum and sum to product. I want to say in the case of, that's for product of sum certainly, but if you're going to derive the other way, it might involve some u substitution. They all still stem from the same thing, some are different formulas. All right, anyhow, take a look at this. If you're going to rewrite the product as a sum or difference in theory, this expression, 2 sine of 5x times cosine, I don't want to put the dots there, but I like to do that. Just explain, when you see an input, however ugly or complicated it is, if you're going to match it up with the appropriate model, the model's all written in alpha and beta. So just realize that this distinct thing, 5x, is really standing in place of alpha, and this distinct thing, 3x, is standing in place of beta. Right? So from our product to sum formulas, right, it's sort of written backwards in this case. Let's see. No, it's good. We'll separate the two, but look for the one that is the right combination. So you have sine and cosine. It would be most closely resembling this one that you see here, sine of alpha, cosine of beta. Right? Ends up being half times the sine of the sum plus the sine of the difference. Okay. All right. Basically, put the blinders on. All right. There's this extra feature here, so we'll just encapsulate this because it's all factors. All right, and we'll tangle with that and then reintroduce 2 later. Right. The model, the identity for this combination of alphas and betas, sines and cosines of which, all right, we would have this. We'd have a half on the inside, all right, and then it would be times the sine of alpha plus beta plus the sine of alpha minus beta. In theory, if alpha is 5x, I'll put a 5x here and there, and 3x beta, you could combine these because they coincidentally are like terms. All right, so the inside guts of this bracket here, and there's still this free-floating 2 on the outside, will blend together later. This is the sine of 8x plus the sine of 2x. If this is 2 times all of those things, we would have to distribute it in theory. Because this, although I neglected to write it, is as part of the identity itself, that, too many parentheses, right? The identity is a half times that sum, all right? So if this is a factor times that factor, all right, we won't have to worry about distributing. As long as I remember to put this again, there's my ding dong, all right? And that's still like that. All right, just cross out the 2's. All right, because 2 times a half is 1. All right, that means that this is what you would end up with: the sine of 8x plus the sine of 2x. Okay. One more the other way. If you were going to evaluate, finally someone gives you a real answer, right? Evaluate this apparent difference. Right? The cosine of 15 degrees, right, minus the cosine of 75 degrees. Right? This is a difference, so we're going to look at it as a product. Why? Because the product is something that is going to involve those angles, and we could finagle what the ratios would be. Remember, we have these special right angles to borrow from, so we could in theory use some combination of them to make 15 potentially and 75. All right. We could think of 15, for example, as being either two things subtracted or two things added. Let's see, what would it be? 45 minus 30, certainly. In theory, it could be 16, 45 as well. Let's call this alpha for the moment, and we'll call this beta. Right? And we're going to borrow the difference that would lead to a product. Right? So if you look at, again, reference, right? If we have, this is cosine minus cosine, we would borrow this version of the sum, and it's technically a difference, right? Difference to product, so this one. Okay. Cosine of alpha minus cosine of beta is minus 2 times the sine of alpha minus beta over 2, because we'll decide whether or which of these in tandem we will use, times the sine of alpha plus beta over 2. If alpha is 15, oh, I wrote it backwards, I'm sorry. Right. This is the positive pair, this is the minus, sorry. Okay. All right. If we're adding them, all right, what's given 15 and 75? Yeah, I was thinking about it backwards before. You actually have less work to do. I'm thinking about half angle. Right? Let's see. 15, right, plus 75 produces 90, right? But 90 divided by 2 is really 45 degrees. It is still nonetheless a special right triangle relationship, so that's cool, because then we could get the ratio without a calculator. All right? If instead we did 15 minus 75, we're going to get negative 60 to begin with. All right? And negative 60 divided by 2 would be negative 30 degrees. Right? That's going to affect the picture here, what we use, because depending upon where you have, if it's just negative 30 in the clockwise direction here, negative 30. Right? This would be still a positive x. We could assume that. Right, for 30, and that would be a negative 1, and that would be a 2. If in theory it was open, this is quadrant 4, right? A negative y value would be over in quadrant 3 as well, but we don't have enough information to decide that, so lots of lahido, leave it alone. All right. Okay. If it's negative 30 and have nothing to go on, you're in quadrant 4. All right. 45 is opposite over adjacent. Opposite over hypotenuse. If it's 45, it's a special right triangle. 45 is 1, 1, and square root of 2. So this is ultimately going to be the square root of 2 over 2 because it would be rationalized. Right? And it's positive because it's 45. Right? This opposite of 30 would be negative 1, so this will end up being negative half as far as we know. And there's still this minus 2 up in the front here. So we can simplify a little bit. Ultimately, this is going to be positive because of that combination of product. And this will cancel one of the 2's. So you're going to end up with the square root of 2 over 2. So was that 0.577 something? Just curious. Square root of 2 divided by 2. Pardon me, 0.707. All right. So you could enter it with your calculator, cosine of 15 degrees minus the cosine of 75 degrees, and you should get the same decimal equivalent. So if this is what I predicted, square root of 2 over 2, which is 0.707 roughly, we get the same result. So it's all good. Okay, got rid of B. All right. We leave it at that. All right, we're at 1 hour and 45 minutes. All right. Thank you guys for listening. This video again was for Tuesday. One more video will be for tomorrow, and that will be for section 10.1 and 10.2. Okay? Thank you guys for listening. Be careful out there.